Computing and Research Center at RTI. Beautiful chair. Thank you for the invitation to be here. So I'll just give a brief introduction to RTI first. We are a private research university in upstate New York. We are around 200 years old. We're established with the intent of advancing science and technology in the US. We have a strong focus on the sciences and engineering. And RPI really pioneers the concept of experiential learning, which is learning by hands-on training. And RPI's major goals for quantum are workforce development, applied quantum computing research, and also achieving the right conditions for HPC-Quantum. So earlier this year, on April 5, we launched our on-campus system, the IBM Quantum System 1. It's located on campus in the Moody's Computing Center, which is a purpose chapel. And on premises, quantum computing at RTI enables us to advance experiential learning by training students. We give them unlimited access to the system. We can explore new applications for quantum devices. We also intend to promote heuristic algorithm development. For example, the QAOA. A lot of times, you can't investigate these things theoretically. You just have to try them out. So this is a good condition for that. Also, for research, I think a lot of grad students, they shy away from experimental research when they're studying quantum computing. If they have unlimited access, we hope that we do that more. And finally, we also want students, we want to give students inspiration to join the quantum workforce. Yeah, we have a lot of visitors every day on campus. We want to come and see the system from a wide variety of audiences. And just as we launched the quantum system, we also happen to have a quantum club on campus that was active. So they like to present to each other, they meet weekly, and they kind of fill in the gaps where lectures and lectures don't meet their needs. So we have a couple of thousand undergraduate and graduate students. And as I said, our goal is to teach students to design, improve, execute quantum algorithms for scientific and engineering applications through an interdepartmental collection of courses. We have some domain experts on campus, and we try to do interactive lectures and hands-on labs in an inclusive learning environment. And if you look at the future quantum workforce, so I guess we can broadly classify in 4 categories. We might have some quantum unaware people who have heard of quantum computing, but they don't know what to use it for. One step above them are quantum aware people who do know some problems where they can apply quantum computing for some speedups. And then above that, we have quantum proficient people who have experience running things, and then we have the specialists who are developing new algorithms. So at RTI, we are trying to enable the students to be at least quantum aware. And if they want to do more, then they have the resources to do that. And this has been a bit successful already. We just had our first undergraduate research paper on arXiv. So Dylan Shields from the physics department, working under Trevor Owen, he was studying the square J1, J2 Heisenberg model. And he was investigating different solvers like VQA or Kirchhoff methods for getting ground state energies. And this investigation, of course, requires a lot of time. So they make good use of that. And we also had another undergraduate research project. We had Paul and Alexander working on the Fabian. So these students, they were trying to run the Hadamard test and quantum phase estimation on our device. And as you can see, the Hadamard test kind of works, but for quantum phase estimation, of course, we are somewhat not in that regime yet. So this was presented at the Duke Quantum Symposium and the undergraduate talks this past week. Now, I'll dive more into the research that we are pushing for. Especially, these are some selected topics where we can see some connection to HPC quantum integration. The first one is the spin boson model, and the rest of them are going to be mostly the electronic structure problem. So the first one is the spin boson model. We have Cameron Cockburn working with Joel Keith. This is an interaction of n spins with m bosons. And for each boson, we have the occupation levels. The first term is the spin term, second term is the occupation, and the third term is the interaction term. And this can be used to model a variety of systems. You can model quantum impurities and also superradiance. And a camera says we can also use this to model noise in quantum computers. Depending on how you set it up, like you can have single spin many bosons or many spins or single boson. And you can map this to a device. There are different mappings for this. The one that we are using is a unary encoding, where each occupation state for the boson, it gets its own qubit. And then for the spins, they are mapped kind of trivially to each qubit. And you use a second order time evolution to do this. This is important because if you have this kind of unary encoding for your occupation levels, then you can apply a configuration recovery, which means that if you sample the states after your trotter evolution, and you see that there are 2 ones or anything other than 1 1 in your state for that for the boson levels, you definitely have incurred an error because it doesn't conserve particle number. So we are kind of pushing for this configuration recovery method to reduce the errors in our simulations. So these are some results without any configuration recovery. As you can see, like they match the expected theoretical results for a very small problem. These are 3 different observables: the average magnetization, the occupation number, and the spin correlator. But we're hoping to scale this up, and for that we're thinking of using the configuration recovery method. And if you want to apply this configuration recovery, instead of getting the expectation values in your quantum system, you just directly sample the bit strings. And then you try to post-process that to recover your samples with the right particle number or etc. You use the information about your problem to kind of fix the errors. And after that, you can compute your observables. And that requires HPC in a lot of cases. The other one is the chemistry benchmarking project. So as Katie mentioned, we need some sort of a consistent way to benchmark problems. We have an entire zoo of algorithms. You have UCC, ADAPT, VPV, so many of these out there. What works on current devices, what is going to work on near-term devices, we need to kind of establish a clear pathway. Usually the results that we see in literature are from simulators. We don't get results from actual hardware. So our approach is to use the W411 dataset for thermochemical reactions. So this is a dataset of about 200 or 300 reactions. And this is usually used to benchmark coupled cluster methods and embedding methods. So this has some history of being used in classical quantum chemistry. And this is reasonably small. You don't have very large molecules. And this is good because you can either use a few qubits or you could use a large basis set and really like crank up the number of qubits that you need to solve your problem. So yeah, this is the goal. And we want to compare this at the end with some gold standard method for classical computing, like coupled cluster. And as Katie mentioned, like I think this can really accelerate quantum chemistry methods. And this is, we're taking a little bit of inspiration from machine learning. There was this ImageNet challenge that was established in 2010, and every year people would send their models and try to benchmark on this standardized data set. And in 2012, finally, the GPUs were used for training models, and we got the AlexNet moment, and then after that, the field completely exploded. So we're hoping that we can kind of accelerate progress in quantum chemistry using this same method. And we are running this project right now using the configuration recovery method that I talked about. In your molecule, the number of electrons has to be preserved, so we can apply the same principle over here. And then you get the samples from one device, and you do a selected configuration interaction for subspace quantum diagonalization problem. So these are very preliminary results. These are not reaction results. These are just the ground state energies. But we can see that when we compare with coupled cluster, the difference is mostly in the positive. And this method is variational, so we definitely know that we're getting a better energy estimate than couple cluster. But of course, this requires a lot of classical computing resources. So this is where HPC-Quantum integration could be somewhat useful. And the next step after that would be to get larger and larger molecules. We are pursuing embedding methods. To give an overview, a rough overview, you chop up your molecule into different pieces and treat each fragment as an open quantum system. And then you solve your fragments with a high-level method, like a more expensive method, and then you try to tie it all together by embedding it into a global object descriptor. So in our case, we want to try and solve the fragments using a quantum computer. And there are a couple of issues with pursuing embedding techniques on quantum computers. First of all, the techniques are developed and refined for quantum chemistry on classical computers. So the data exchange between your fragments and the environment, it looks a bit different, because I/O from a quantum computer isn't the same as what we do classically, right? So we are hoping that the findings that we get from our benchmarking project are applicable to the embedding project, because the fragments are going to be somewhat arbitrary. Most of the papers that you see out there are for some particular molecule that people are pursuing. That's very important. But we want something more general. So to scale this up, of course, we need HPC on both the high-level method, if we use some SQD subspace type of method. And for the high-level method, so for the low-level method for the environment, if we really go for the large number of fragments, we will need HPC over there also. And then finally, taking it one step further, so RPI as an engineering student, a lot of times I get asked, like, what can I do for an engineering problem with quantum computing? Multi-scale modeling, I think, is a very good example. We have these ab initio methods at the very bottom, and you connect them to larger and larger scales until you solve your big microscale problem. And usually the workhorse for this is a DFT, and these system sizes are pretty large. So we're hoping that by applying some embedding techniques, we can start to think about using quantum computers for these problems. And of course, if you use DFT, then correlated problems or excited states are often out of reach. So we're hoping that the embedding and the benchmarking projects help us pursue this goal further. So this is very much in the theoretical phase right now. But in this project, the HPC component is applicable at each scale, starting from the quantum device all the way up to microscale projects. And this is just like one example of some multi-scale problem that can be pursued using quantum computing. So to give a bit of context, so this is a mechanical engineering problem. Over here, we have this sample of titanium. You stretch it, and you keep stretching it until it breaks. And you keep a record of the how much it stretches, the total strain. And this is the stress that you're applying. Now, titanium is notoriously difficult for being a very tough material to machine. But experimentally, it's found that if you pass an electric current through your sample, suddenly it becomes soft. Now, to rule out that it's not just because the sample gets hot when you run an electric current through it, you run a temperature match study. And when you try to match the temperature, you see that passing an electric current actually further softens the material. And this is a very relevant problem because the entire area under your graph that you see over here, this is the amount of energy that you need to put in just to break this object, and or in a practical case, like machining your object. So by reducing this to this smaller area, I think this has a great impact for a very, very real world problem, a very classical problem, but maybe this is described by, maybe this can be explained better using a quantum computer. And this is a multi-scale problem because you can see that the crystal grains are very different for the temperature match study and the electric current study. So with the electric current, the grains become long. So yeah, this is a very good target for a multi-scale modeling problem. And just taking a quick sidebar, so I think there is this concept of concurrent or simultaneous engineering. In sequential engineering, you just develop things one step at a time, but in simultaneous engineering. You try to reduce the lead time. You work with a smaller team. And there's a lot of exchange of information between different steps. And you try to conduct each step at the same time. So it seems like for electronic structure flow, for electronic structure problems, we do have this kind of concurrent flow where we're sharing information between different types of problems. So yeah, we're hoping that we kind of reduce the time to get some kind of advantage out of these devices for real-world problems. So for a small private university, RPI has always had a large appetite for computing. We've had 2 generations of the Blue Gene system, and right now we have the AMOS system from IBM. So we call this Baby Summit because it's configured pretty much exactly the same as a Summit, just with a fewer nodes. These are Power9 chips with 100 GPUs, and at its debut, it was 23 on the top 500 system. On the top 500 list. We also have a couple of Grace Hopper nodes, and we also have our quantum system on campus. So this is a good setting to start looking at HPC quantum integration. Just to give a little bit of an overview, we have 252 nodes of these Power9 processors, and there are 6 GPUs on each node. We also have an additional cluster, which is x86. It has the same V100 GPUs, but we have 8 of them on each node. This is very useful because trying to run things on the Power9 chip can be sometimes difficult. So you can just run things on x86. It's the same architecture as your typical laptop. So, yeah. And the supercomputers are located at the CCI, which is a couple of miles along the Hudson. So the quantum computer and the supercomputer are not co-located, but we do have a direct 10 gigabit link from campus to CCI, which you want to use to set up this integration. And as I said, the immediate application is we want to apply these configuration recovery techniques and these subspace quantum diagonalization methods to leverage HPC for our quantum simulations. And downstream, of course, we want to also use embedding and multi-scale bonding in our HPC framework. So we are setting up the integration. We want to set up the quantum device as a STERM resource, and this is a joint effort between IBM and RPI. But unfortunately, over here, I'll have to put a hard stop because I asked for permission to talk about this, but it seems like the lawyers at RPI and IBM have kind of not conversed. And since this is an export control technology, like I don't want to get in trouble. With that, 2025 is the International Year of Quantum Science and Technology. And hopefully, the years coming here, hopefully we're more productive in the coming year and we make some progress. So thank you for your time. And if you have any questions, please go ahead.
I wonder why you decided for this application to use the couple cluster and also the embedding theory, because from a classical point of view, couple cluster is good for dynamical correlation, and actually this is not a problem in chemistry at all. Problem is static correlations. And also embedding theory is also for couple cluster for system with dynamic correlation. And again, this is not a problem in classical. So why you are trying to benchmark this quantum?
So I guess one of the reasons is because of the I/O issue. So with couple cluster, we're trying to use unitary couple cluster. That way we can just use the coefficients from unitary couple cluster and embed them into the.
Yeah, but I know that they are using it in quantum unitary. In classical, it's not variational. It's just couple cluster. But at the end of the day, you are spending the same Hilbert space, right? Single and double. So you're not gonna get any new like improvement, right? There is some improvement. It like you can do really like multi instead of single reference, multi-reference. But also when you think about this from quantum resources, you are gonna need more resources. And also with this BQE and optimizing those parameters, how are you gonna scale this up? Similar things when you have the embedding theory, we have the classical embedding theory, and it is also working. We can simulate large system with couple cluster, And doing it in quantum, I mean, dynamic correlation is not a problem in chemistry. These problems can be solved. So I'm really wondering why people are like pushing on this embedding theory, because embedding theory is not a is working in classical, and problem is dynamic correlation is not a problem in quantum chemistry in general. I think a problem is static correlation, where we need to use like SCF, where things scale exponentially, and those are the challenges in chemistry. And you can look at some publication about how using embedding theory is actually like for chemical reactions, it's actually for static correlation is failing. So I really wonder why people are pushing to understand and benchmark
So
on
in
that.
this case, I think we're not completely converged on using UCC or embedding UCC into some environment. We're looking at different methods. And the SQD method that we have, this is actually an SCI, get SCI coefficient on this instead of the cluster amplitudes. But I think I can relay your question to Fabian, who is kind of leading the theoretical side of this. I'm more on the implementation side of this. But yeah, that's a good question. But we are looking at like different kinds of.
Much simpler question. About, I would like to know, how do you give user access to your quantum computer?
Right. So on campus, like all the students, they can just ask any faculty member to sign a form for them. If you want to get access as an outsider, then you can just send me an email and I can set that up.
What's your protocol for keeping the machine operational? Like if something goes down, do you have IBM folks who will
Yes.
regularly recalibrate?
Yeah, they do firmware updates and calibrations. I think they calibrate it maybe once every couple of days or maybe once a week.
Okay, and that's enough.
Yeah.
Do they have to be there in person?
So for calibration, I think it's just like an automated routine. The machine goes down and you just collect data and just that to calibrate.
Okay.
But sometimes when you firmware updates, it goes on for several hours.
A question, follow up to Jan's question. You said that just I have to send you an email and then you give me an access.
Just like it has to
Is
be.
it as easy as that?
Not as easy as that. Like,
Do you charge for it? But I know, because I know that IBM charge you guys for QAUs, which is $1 million a year.
Yes, it's very
So
expensive.
are you that generous to give us free?
It has to be some interesting project. There has to be an RPI counterpart to that. I can assign you with some researcher who is working on the same project and we can collaborate.
Okay. I will need your business card.
How many qubits?
127. 127. Superconducting.
This is on the Eagle?
Yes. We're hoping to, we'll be getting an upgrade either next year or the year after. Yeah.
And these are physical qubits, not logical.
Yes, physical. Yes.
How many logical qubits with all error?
Oh, right now, we don't have logical units. That's like way down the line. Yes.
I will ask more questions, but feel free not to answer. So, so you have this machine for like half a year or a year. So could you tell us what is the real uptime? Does it, what fraction of time it's down? Does it kind of saturate at some value?
Right. We just launched in April. Initially, for the first few months, we didn't have a lot of users, but since the semester started and courses are using this for the students now, maybe we have a queue of like 5 or 6 people, something like that, but it's very small. So it's very easy to run jobs.
Well, I was asking uptime. So how often the machine is down?
Oh, very, very rarely. Maybe once a week or mostly it's operation. One more question.
So usually when, let's say, someone buys the HPC system, he wants to make sure that the system has, it's working correctly, you know, the InfiniBand and the memory and everything. How do you make sure that the quantum computer is working correctly? Are you just using the calibration by IBM, or do you have your own testing that you make sure the system is?
Right now, we use the calibration by IBM. I think you can use your own calibration too in the device. I think it might have that flexibility. You can also program the pulses. It does have that level of control too. So if you're like more interested in like hardware level of studies, then yeah. Everything I presented was more on the like algorithmic level. So we just take that calibration and just.
And do you provide to the students or the users a more lower level access?
Yes, as I said, you can do a pulse level.
And have you used it or not?
I haven't used it, but I know there are people on campus who do that.
Curious question also. Like, me and Yan are in the same wavelength here. When there is when there is a situation that requires IBM engineers visiting your site to maintain or do something with the machine, do they allow any of you guys to be there with them, or
No,
it has to be
So,
only IBM?
yeah, it's completely IP related, so yeah.
So that kind of knowledge is not
Yes.
revealed.
But for the Slurm integration that we're doing, we are working on together, so yeah.
Are you allowing on that for any platform, or it's like to develop the algorithm, or it's gonna be only using Cascade? Or you are going to be open to allow users to develop their algorithm with whatever platform they have and maybe.
Yes, so as long as your job is like an open chasm environment, then you can also do
converting
that.
as long as we can convert circuit, like.
Yeah.
Okay.
Also, you can do pulses, like I said, that's like.
Okay, I promise this is the last question, but is IBM software stack on your machine keeping up what IBM is running on their facilities? Or like are you a version behind, or you have always, if they update, you update too, it's guaranteed?
Usually we're at the same level, but for some very minor things like just there's this backend.run function. Right now we have classes running, so we kind of deferred it till the end of the semester, but something very minor like. But most of it, the Cascade IBM runtime is going to work like in this.
We can thank the speaker and then ask more questions during the coffee break.